So, ladies and gentlemen, once again, every single one of you is welcome. We are starting some of the applications of linear programming, and we'll be starting with a topic known as the network flow models. Network flow models. So, as always, if you have a question, type it in the chat there or raise a hand and let me know. What is a network? What is it? A network is an arrangement of branches or paths connected at points, which we call nodes here, okay, via which one or more items move from one point to the other. So I want to believe that most of you know about Okpongolo Junction. Okpongolo Junction. Now, the Okpongolo Junction is a traffic light that connects the University of Ghana with the Okpongolo town, with the Medina Road, and with the Accra Road. Now, that very junction is a node. It's a node. When you get to the Accra Mall, there is another node. And between the Accra Mall node and Okpongolo Junction is an arc or a branch, a path. And so you are able to carry human beings, items, or anything from Okpongolo to Accra Mall through the branch, the arc. So a node is connected by an arc, or two nodes are connected by an arc. And the network diagram that will show it will give you a visual representation of everything that we are discussing. Okay. And this is a typical example of a real life situation that we have. So what is a node? A node, they are usually circles, junctions, locations, vertices, points. And I've given you an example, it's intersections of a street, okay? Road terminals, terminal one, terminal, the terminals. Okay? We can have supply node and demand nodes. Okay, we can have a supply node, a demand node. A supply node is the one that is supplying the items, and demand node is the one receiving the items. What items? It can be anything from human beings to cars to, anything. But before you can supply from one node to another node, before you can supply from a supply node to a demand node, you need to pass through an arc, a branch, which shows you the lines or the directions. And so the network flow models, what it does is that you use that to be able to, these models, you use that to be able to understand the goal of minimizing. And of course, it's bearing its name with the principle of linear programming. So your goal is to minimize the distance traveled, or your goal will be to minimize the cost of traveling across different nodes. And that's the goal. And there are several models that have been developed: the transshipment, assignment, shortest path, generalized network flow, minimum spanning tree, project scheduling, and all of that. Of course, we'll not do everything. Okay. So understand what a node is, understand what an arc is. I'll be using that a lot. And if you are ever taking notes, put this down, even though we'll come back to it. The decision variables in a network model are represented by the arcs. The decision variables are represented by the arcs. Okay. The decision variables, they are usually represented by the arcs. And then the constraints are denoted by the nodes. So the nodes represent the constraints. And then the arcs represent the decision variables. You're going to love this. You're going to love this. I mean, there's no question. You're going to love this. Okay, so let's start looking at some of these principles. So let's look at some few features of the network optimization model. So the idea is to determine how many or what is the number of items I'm going to flow or move across the axis. Okay, and I've already indicated that we have supply nodes and then we have demand nodes. In fact, the gap between supply node and demand node is the transshipment node. So the transshipment node, they don't receive, they don't send, but they do both. They receive and then send at the same time. Transshipment nodes. So when you take Okonglo and Accra Mall example that I gave, if the thing doesn't end at Accra Mall, but it continues to 37, okay, it continues to 37, then Accra Mall junction becomes the transshipment node. Okay, it becomes a transshipment node. So this is a typical diagrammatic representation of everything that I'm saying. So you can see, watch the arrows carefully because it's not just the lines, but the arrows as well. So if you look at a demand node, the arrows are entering into it. Okay, the arrows are entering into it. It is not giving out. There is no arrow leaving this demand node. But look at the supply node. There is no arrow coming into it. Okay, there is no arrow coming into this supply node. No, there is none. There's no arrow. There's no arrow at all. Coming into this supply node, there is none. And because there is no arrow coming into the supply node, that is why it's a supply node. But if you look at the transshipment node, there's an arrow coming into it and there's an arrow leaving it. Okay, so you have an arrow entering into the transshipment node and an arrow leaving the transshipment node. And so clearly, you can see that the transshipment node is both receiving and then supplying. So this is just a quick diagrammatic representation of everything. Okay. So please note the arc represents the decision variables and the node represent the constraints. Now the node numbering is a very nice way to identify the decision variables. Okay. The way we number the nodes is very, very nice. Okay, and we're going to look at that. We use something like Xij to represent the number of items that are taken from node I to node J. Okay, so I'll give you a typical example of what I'm indicating here so that you can appreciate it even better. So let me just take this situation here. So in this situation, I'm just going to create some circles. Okay, so this is one circle. This one obviously is what? Is a node. Okay, this is another circle. Where is that? This is another node. Okay, and that's another node. Okay, and that's another. We'll drop the transshipment for now. Okay, so these are the nodes that we have. So we have all of these nodes that are hanging in there. Now, if you look at these nodes, okay, that I've indicated, you wouldn't know which one is a supply node or a demand node unless I use an arrow to represent it. Okay, so let me just pick an arrow and try to showcase where it is moving from and where it's going. So you can see from here, okay, with the arrows that I've actually indicated, you can see from here. Let me just delete it and then do it again. Okay, you can see that this, the fact that it's moving from left to right here, makes the left one a supply node and then the right one a demand node. Okay, it makes one a supply node and then the other one a demand. Of course, we need to number them. And so inside this supply node, inside this very supply node, I can decide to number it as 1, okay, and number this as 2. Number this as 2, number this as 3, number this as 4. So number 1 is a supply node. So I will just put something on top of it as S and this as D together. Now the amount of what I'm transporting from this supply node to the demand node. So the amount of what I'm transporting from this supply node here to the demand node, I need to write it on the side. Okay, so let me just write the amount of what I'm transporting there. Okay, so I can say that I'm transporting 100 items here. Okay, and I'm transporting 200 items from here. I don't know the items, could be bags of rice. Okay, and I'm transporting them to these junctions. Okay, these demand nodes. However, how much is this number 3 expecting? Well, number 3 is expecting 150. Okay, and then this one is expecting like 200. Okay, no, let me say 300, something like that. So you have this going on. Now, what we are saying is that the 100 that we have here, the 100 that we have, the 200, the 150, and the 300, they will now make up the constraints very soon. So when we are looking at the constraint, or more or less the right-hand side of the constraint, these become the constraints on the right-hand side. Okay, keep that in mind. Now, what is going to represent the decision variables are the arcs here. And so we need to label this arc. We need to label this arc. And what we indicated was that Xij represents the number of items moving from node I to node J. Now, so let's assume that I'm moving from node 1 to node 3. My decision variable is going to be what? From node 1 to node 3, my decision variable is going to be what? So it's going to be X13. That's how it's going to be, X13. What about from node 1 to node 4? It's going to be X14. That is a decision variable. Okay. What about when I'm moving from node 2 to node 3? What do you think the decision variable is? Type it there for me. Okay. If I am moving from node 2 to node 3, okay, along the arc, okay, excellent, excellent, excellent. Okay, in fact, most of you are writing the correct answer, starting with beta, Leonie, and all of that. So you get X23. Okay, and then the decision variable from node 2 to node 4 is obviously going to be X24. So when I say that now put all of the decision variables together, then you know what it means. This is it. Basically, this is it. However, there will always be a kind of a cost associated with moving the items from node 1 to node 3. Okay, so there may be a table that is telling you the cost associated with each movement. And so when you have the cost associated with each movement and you are writing these costs, you need to attach the cost to the nodes. So let's say that the cost from 1 to 6 is, say, let's say 5 cities. You are now going to attach 5 in front of the X13 so that you have 5X13. Let's assume that the cost associated with moving from node 1 to 4 is 9. You write 9 attached to the X14, so you get 9X14. So eventually, when we are now going to minimize this cost, okay, then our Z min is going to be equal to the 5X13 plus 9X14, okay, and then you continue with the numbers that you would have given for this. Imagine this was 3, Okay, you add that. Imagine this was 6, you add that as well. So that is how you actually indicate this. So remember, the acts are the decision variables, there's nodes are the constraints. Okay. We'll come to that. But the best way to come to that is actually giving you a typical example. Okay. So what I'm now going to do is to give you a typical example that will catch up everything. So you can see that the CIJ is a cost or the money or the distance or the penalty for using that route of node 1, node I to node J. So I was talking about costs, but it could be the distance traveled. It could be the penalty you got to incur for passing through that arc. Okay. For maximization problems, this is what we are going to have. We are going to maximize the cost multiplying the decision variables, just like I said, and then you sum them. And you can remember that in my own, I was summing them. Okay, that's a maximization. For minimization, we're going to minimize the cost or the money or the distance or the penalty multiplying the decision variables. Okay, so remember the acts are the decision variables, the nodes are the constraints. In particular, there must be one constraint for each node. There must be one constraint for each node. So guys, let me just take you back to this. How many constraints do you think are shown here? How many constraints are shown in this? Who can tell us? How many constraints can we count here? There we go again. Priscilla, George, excellent. So there are 4 constraints. There are 4 constraints here because there are how many nodes? 4 nodes. I mean, you guys are incredibly smart, incredibly wonderful. Okay, so let's move on. So we are going to now look at the 3 special types of linear programming which adopts the principle of this network flow models: transportation, transshipment, assignment. I'm going to first walk you through the transportation, and then we shall extend it to the transshipment and then look at assignment. Okay. All right. So they need specialized algorithm, procedural analysis to solve them as far as efficiency is concerned. So let's look at transportation. So the transportation simply says that we have a product which we are transporting it from a source to a destination. That is from a supply node, which is a source, to a destination node, which is a demand node. Okay. And we want to do that at a minimum possible cost. And each source is able to supply a fixed number of units, okay, not variables, where you change it. No, anytime you are supplying from the warehouse in Tema and taking it to the warehouse in Spintex Road, anytime there's a fixed number of units of product that you supply, and each destination is also receiving a fixed number of product. Okay. And each unit incurs a variable cost of CIJ. So the linear programming will have constraints for the supply, and then we'll also have the constraints for the demand. Okay, because you can see that the number of constraints will determine the total supply and total demand nodes. Now, here is the thing. There are 2 kinds of constraints. One of them is a balanced transportation model where the total supply equals the total demand. Now, let me give you an example. A balanced transportation is where the total supply equals the total demand. Now, look on the screen here. The total supply is what here on the, if I should do an equality, the total supply is 300. Okay, so those are 300 items for the total supply. What is the total demand there? It is 450. Okay, so will this be a balanced transportation model or it will be an unbalanced one? Will this be a balanced or an unbalanced one? I'm getting some incredible answers here. Okay, it is unbalanced. It is unbalanced. There's no question about that. This is an unbalanced transportation model. Okay. However, you should know that we can also have a balanced transportation model. So the fact that you understand it here is important. Now, when there is a balanced transportation model, all the constraints are going to have equal to. So for example, if you are writing the constraint for 100, all you are going to do is to look at the acts that are leaving it and check the decision variables there and add them. Check the decision variables there. It's not the cost. You don't add the cost, but just the decision variables. So which decision variables are leaving the node 1? Well, the first one is x13. So we'll write it as, let me write it here. Okay, because it's x13. Okay, I think somebody is even writing it already, which is good. Okay. So you write it as minus x13. Minus simply because it's leaving. Then the next one, which is leaving it, is minus x14. Now, the question is, are we going to use less than or equal to 100? Remember, the 100 is going to be the items. Okay, so all of this should be something 100. And the question is, are we going to use less than or equal to, greater than equal to, or equal to? If it is a balanced transportation model, it has to be strictly what? Equal to. That's what we are saying. If it is a balanced transportation model, it has to be equal to. If it is an unbalanced transportation model, it will be less than or equal to or greater than or equal to. That's how it's going to be. Less than or equal to or greater than or equal to. But we'll come back to that. Of course, this one is going to be either less or equal to or greater or equal to. That's how this one is going to be. Of course, the 100 is leaving, so you also have to bring the minus 100. Of course, when you apply plus, when you apply negative to all of them, you are going to get plus. Okay. Now, the symbol minus is just indicating that it's leaving. It's leaving. Okay. So we've not decided yet whether it's going to be less than or equal to or greater than or equal to for an unbalance. We'll come to that. Yeah, I'll explain that to you for now. Okay. So on the basis of this, now, these are the notations. These notations are just scary notations, just to let you know that you are doing a higher level postgraduate course. Okay, so don't worry. The M is representing the number of supply, number of demand. Xij is the decision variables. The cost is Cij. The Si is the supply. That is the one on the right hand side. Okay. The Dj is the one on the right hand side as well. The coefficient of the decision variables in the rows are the ones you see here. So if we were to do a general transportation model, this is how it will be, okay, for minimization. So we are going to minimize the sum of all the items, okay, where do you have a cost multiplying each of the decision variables, subject to these constraints, okay, subject to this constraint, where the supply is this one here. So the things that are going here should be less than or equal to the supply. And the demand, the item should be greater than or equal to the demand. Of course, those decision variables will still have the non-negativity constraint being shown down here. Okay, so you still not forget your non-negativity constraint. You will still have to have that in mind. Okay, non-negativity constraint. Okay, let's take a typical example. This is a real life typical example. It will help you. It will help you. So let's read it. We are going to answer this question as a way of understanding everything. Wheat is harvested in the Midwest. It's stored in grain elevators in 3 cities. So the wheat are in grain elevators in 3 cities: Kansas City, Omaha, and Des Moines. I don't know how you pronounce that word carefully, but you can shorten it and just say it here. Now, what is the next thing? The elevators that you have, the elevators supply 3 flour mills, which are located in Chicago, St. Louis, and Cincinnati, depending on where you were born. It says Cincinnati. Now the grain is shipped to the mills in railroad cars. Okay. Each car is able to hold a 1 ton of wheat. Each elevator supplies the following number of tons of which the mills every month, and the cost associated with each is following. So we are going to see the table that depicts that. So you have the elevator in the first column, and these elevators are 1, 2, 3, Kansas, Omaha, and DM. And they are supplying 150 tons of wheat, 175 tons of wheat, 275 tons. Okay, these guys are supplying these tons to the mills in Chicago, in St. Louis, and in Cincinnati. So we are moving from 1, 2, 3, going to A, B, C. But remember, Kansas City will supply to all 3. Omaha will supply to all 3, or is supposed to supply to all 3. DM is supposed to supply to all 3. And the Chicago is receiving 200 of the tons, 100 of the tons from St. Louis, 300 of the tons from Cincinnati. So this is it. So you can quickly see your supply node and the demand node there, don't you? If I tell you to actually draw this, will you be able to draw it? Of course you will. But there's a cost associated with sending the items. So anytime you're sending from Kansas City to the A, B, and C, the 3 cities, okay? Anytime you're sending it from there to these 3, the cost associated with sending it to Chicago is $6. The cost associated with sending from Kansas City to St. Louis is $8, and to Cincinnati is $10. The same way Omaha is supplying to all 3, and the cost associated with each one of them is that. DM is supplying to all 3, and the cost associated with it is shown right there. So, ladies and gentlemen, the question is a very simple question. Draw. Okay, let's go to the question now. Define the decision variables for this transportation problem. Define it. Well, it's a thing to define. Okay, how would you define it? There are 2 ways of defining the transportation problem. Okay, there are 2 ways. Let me just take you back to our board. So we've already indicated that you have X, I, J. Okay, and that is one way of defining the information content here. So you will say that let Xij be the number of tons of wheat, okay? Number of tons of wheat transported from, you can just say transported from node I to node J. That's one way. Okay. Transported from node I to node J, where I is not equal to J. Okay. So you have to indicate that. Okay. Where I is not equal to J. Now, this is just a mathematical way of representing this. Okay. But you can decide to make it complex and be specific that, let the number of XI be the number of tons of wheat from the elevator to the mill. Okay, that is one way. So that you don't bring the node. So you say from elevator to the mill, or from elevator I to mill J. So that you are kind of specific. And then you now define the I. Okay, where I is equal to 1, 2, and 3. And the J, if you can remember, the J were A, B, C. So you have A, B, and then C. So this is how you, in fact, most of the time, the way you define the decision variable is going to be similar like this. It's not going to be changing too much. Okay. So if the number of supplies are 4, then you are going to have 1 to 4 instead of 1 to 3. And the rest will continue. So this is how you define the decision variable. If you don't get it, just raise your hand or type it for me, and then I will address it. I think this is cool. It's cool, isn't it? Okay. Right. So now that we've been able to define, let's go to our next part of the question. Okay. Question says, next part of the question says, develop a network graph of this problem, showing all the costs. Okay, showing all the costs. All the costs. And I like this. Okay, I like this whole principle of showing all the costs here. So you got to show all the costs. How do you do that? And then show all the decision variables. So we're going to draw it. So I want you to start drawing it using the principles here. Can you do that? Can you draw it? Well, you can. Why not? Okay. So let's try and do that whilst you're doing it together. So you have to, first of all, create your circles. Now you have to know how many are the supplies and how many are the demand. There were three. So the first thing you want to do is to create this. Okay, you create this. So you create the first one here. You create a second one there. Now these things may not necessarily be, up to scale. So you don't have to worry so much there. Okay, you create a third one there. You create the next one here. Because we know that the demand nodes are also 3. So you just have to do that. Okay. That's it. Now let's go and show something. Okay. When you go to the port, you know that you are supplying 150 from Kansas City, 175, 275. Okay. These are 1, 2, 3. So you just go and then you do the same thing there. You try and then negotiate the same situation there. And so you have to write the numbers right here for them. Okay. So if indeed this was 150, you just write it on the left, 150, 175. Okay. And then the other one, I think is 275. 275. Then for the supply, for the demand, okay, the items were 210, 200, 100, and then 300. So that's what you indicate. Then you start indicating your arrows. Your arrows. Now that's where it is interesting to do. So you indicate your arrows, but before we indicate our arrows, I just must say that we need to just write the names into it. Okay. Now there are one ways you can do. You can put numbers for each one of them, so that this one becomes number 1, number 2, number 3, number 4, going. Okay. But in this very one, there was A, B, C given to us for the supply. So I just want to use that one. But please note that you can do, in fact, let's do how it's supposed to be nice. Okay, so you can do 4 and then 5 and then 6. But you should know that the 4, 5, 6 are your demand nodes. Okay, so now that you have that, you can now add in your what do you call it? You can now add in your acts. So remember, the acts are moving from 1 to 4. Oh, okay. You have your acts that are moving from 1 to 4. You have another act moving from 1 to 5. You have another act moving from 1 to 6. Believe me, you have to write these things before you even continue. Because once you do for the first one, go and write the cost and then the decision associated with it right there. Okay. Now, the cost for each one must be on the edges, and the decisions must be towards the end. That way you separate them nicely. Okay. So the cost must be on the edges, then the decision. So let me show you the cost for the cost associated with moving from Kansas City 1 to 4, 5, 6. Okay. Remember, I have called mine this 4, I've also called this one 5, a B5, and I've also labeled the C as 6 in hours. So we have 6, 8, 10. Those are the costs. Okay, 6, 8, 10. So when you go to your formulation, you write what 6 for this, you write it at the edge, 8, and then 10. Just like that. Okay. And now we are going to add the decision variables. How do you add? Remember, it's from 1 going to 4. So the decision variable, how are you going to write it? You're going to write it as 1 going to 4. So you will have x 1, 4. That's for the first one. Okay, the second one is x 1, 5. Then the third one is x 1, 6. Okay, so now, I remember you got to learn how to draw this. Okay. Once you've written this, then you go to the second one, because if you try to do all the acts, sometimes if you don't take it, you lose track of which is which. So that's why you got to label it before you go to the next one. So now you go to the next one, is from act from 2 to each one of them. So, okay, so you take your number 2, going to this first one, number 2, going to node 5, and then node 2 again, going to node 6. You see now they're a little bit getting a little bit confusing, which is why you have to. And then you go and then attach the costs associated with this. Okay. And when you go up here, you see that the costs are 7, 11, 11. Okay, 7, 11, 11. And the last one will be 4, 5, 12. So you now go and then you indicate those costs there. Okay, 7, 11, and then 11. Now you have to indicate the decision variables, and it's 2 moving to 4. Okay, that is from 2. Okay, 2 here, moving towards 4. So the decision variable is going to be x 2, 4. Okay, I'm just slowing down for you to love it. Okay, so now you're going to have x 2, 4, and then x 2, 5. Okay, and then you're going to have x 2, 6. So those are the decision variables. And you can do the same thing with the third one, which is node 3. And then you can do that. So let me just show you how this will eventually pan out. So you can see how this is now looking like, all right? Of course, this one, I've taken my time to beautify it. The most important thing is make sure you've written your number of items being supplied on both sides, indicates the inside a ring, inside a node, whether it's node 1 or node 2 or not. And you can see that here I have A, B, C, but we use 4, 5, 6, which I said is probably the best way to go. Okay, there's no problem at all. And then, so this is just for the first node, Kansas City. Okay, you can write the names below it. Okay, you can write the names below it to beautify. And then you can now have the final one, which is this development. I'm sure you can do it. I'm really, really sure you can execute this on your own beautifully. I mean, I want to believe that some of you have practically been doing this whilst I'm doing it. Because if you are practically doing this on your paper whilst I'm doing this here, I guarantee you are on in a comfortable lead. Okay. All right. Now that you formulated this, let's ask ourselves whether this is a minimization or maximization. When you go to the question, you will note. Okay. Okay. Develop. Now look at the last part. Okay. How many tons of wheat should be transported from each grain elevator to each mill every month in order to minimize the total transportation cost? So this is a typical minimization. So we got to write our objective function. Who can guess how the objective function is going to be? Now, anytime you are writing the objective function, your eye must be looking at these costs that you wrote, and your eye must be looking at the decision variables that you wrote. So how is it going to be? How is it going to be? Well, if my eye is looking at it as it is here, okay, I can just write it like this. if your eye is looking at it, you can just say that, let's have Z max, okay? Or here you can use C min, anything, you know, Z max, Z min. So you can have Z min equal to, the first one is 6x1a. That is what it is here. But of course, yours, if yours is there, yours is going to be 6x14. That's how yours is going to be, plus 8x15 plus 10x16 plus, you keep going, then you go to number 2. Number 2 is 7, 11, 11. So you get 7x24 plus 11x25 plus 11x26. Okay, plus, then you go to the third node. And then you write that one to 4, 5, and then 12. You add all of that. And that becomes your objective function. Okay, that becomes your objective. I'm pretty sure that all of you have executed it very, very, very nicely. Okay, so once if you happen to do that correctly, let me just clear this. Okay, if you happen to do that very correctly, you're going to have something like this. You're going to have something like this here. Okay, and in here, let me just show you something. In here, you can see that you have the Z min there, the X1A, which is what we used for this one, but it's the same thing. And the key point is knowing that you have the numbers all well written down, all well written down. So this becomes your Z min. Of course, the next thing will be subject to the constraint, subject to the constraint. Okay. And so how many constraints are we going to have here? Can you write it down for me? If you can remember, of course, you know where we are coming from. In total of how many constraints, if you look at the graph, you will definitely know how many constraints you're going to have. So how many constraints are we going to have here? Somebody says 4. No. Oh, 6. 6. 6. 6. Exactly. The majority of you are saying 6, and that is true. We're going to have 6 constraints. So what I'm going to do, guys, what I'm going to do is to do the first constraint for you, okay, so that you can appreciate the other ones. I'm going to do the first constraint for you. Now, for you to be able to do the constraint, you need to have in your eye the graph. So let me just show you the graph. So this is a graph. Okay, this is a graph. This is a graph that we have here. Okay, you can see the first one there. Now, how do we write this constraint? Well, you're going to write a constraint for this one, the first one. So you look at the acts that are leaving it. Oh, by the way, you need to identify whether it's a balanced transportation model or it's an unbalanced transportation model. And when you look at 150 plus 175 plus 275, that will give you 600. When you look at 200, 300, 200, 100, 300, that will also give you 600. Okay, so this is balanced. And so because it's balanced, we're expecting everything to be equal to. So if we are to write the first one, the first constraint, okay, if I'm to watch it with my eye and write it whilst I'm watching it, okay, sometimes it's nice when you are writing it whilst you are watching it. It sounds quite nice like that. Anyway, so the first one, you look at the acts that are leaving number 1. I'm just going to do the first one. The acts that are leaving number 1 in this context, in your case, if you wrote yours, is going to be X1, 4. Okay, remember, it's all going to be negative, so I'm going to leave it as positive. Okay, X1, 4 plus the next arc that is leaving it. Okay, in fact, you will see it them here. So this is the first one here. Okay, The next one that is leaving it is this. The next one that is leaving it is written here. So you just have to follow through. Okay. So you're going to have x15 and then x16 equal to, then you write a number. Okay. The number that is here, which is 150, you write that. So equal to 150. And that becomes your first constraint out of the 6 constraints. Now, can you do for the other ones? If you can do for the other ones, type yes. Let me be sure that you can do for the other ones. Can you do for the other ones? Okay. Let me see how many yeses I'm having. Okay. If you can't do it for the other ones, just type no. Okay. If you cannot do for the other ones, type no. If you are triple confused, type 0. If you are triple confused, type 0. Or majority of you are typing yes. That is very good. Majority of you are typing it. Okay. So you should be doing this on your own. I'm giving you some single time. You should be doing this on your own. Okay. You do this. In fact, try the second one on your own. Convince yourself on your own. Somebody can even type the last one for me. Type the last one for me. Of course, if you are typing it, it means that you just have to write X1 for they will all be the same thing. It wouldn't be a subscript like mine is a subscript, but that's okay. Okay. Okay, that's okay. And when you do that, I want to see whether somebody will be able to type the first, type the second one or the last one. Somebody should type the second one or the last one. Don't just type yes, yes, yes. I want to be sure whether you are truly be able to do that. I want to be sure whether you truly. Oh, fantastic. Somebody just did the second. Oh, no, the third one. Let me see. 3, 4, 3. Oh, fantastic. Okay. Somebody did 120. Where is the 120? There's nothing 120 there. Okay, Abigail, check yours. Okay. Somebody did the second one. Okay, for the second constraint here. Oh, that's fantastic. That's beautiful. That's excellent. That's excellent. So, oh, that's good. Okay. The one who did the 120, you're the only one who made yours wrong. I don't know which one you were doing, but it looks like you were doing the 275. So check that. Okay. So if you are able to go through this and execute all of them very nicely, eventually this is what you're going to get. Okay. Eventually, you're going to get a beautiful, formulation like this. A beautiful formulation like this. And you can see clearly the beauty of it. So you have your maximize, okay, subject to all of the 6 different constraints. Of course, there's one more constraint you should never forget, the non-negativity constraint. Okay. The non-negativity constraint. So if you look at this, the non-negativity constraint is here. This one. That is a non-negativity constraint. And so it's very important that you always do not forget it, because sometimes when you're in the mood and you're enjoying everything in the mood like that, okay, you forget this non-negativity constraint. You do everything, then the most important thing, you leave it. Xij is greater or equal to 0. You got to write that. Where, of course, we've already defined the x's up there. So you just have to indicate that this is it. And that is how it becomes. Fantastic. Now, the next thing is to solve it. Of course, you will only have to solve this thing in Excel. Okay. You will only have to do that in Excel. Now, but before then, let me ask you some few questions. What if demand was greater than supply? What would have happened? What if the total demand, which was 600, was greater than the total supply, which was 600? What if that demand at Cincinnati was raised from 300, if you can remember? Okay, Cincinnati, okay, they were expecting this 300. But what if they raise their demand from this 300 and they take it to 350? What happens to the totals? The totals will change. It means that demand will now be more than what supply. Do you agree with that? Exactly. So we got to now decide on which symbol we are going to use. Of course, you know that you're going to use less than or equal to or greater than or equal to, but which one? Because now we have an unbalanced transportation model. So that will result in the following. Now, the supply will not change the equality sign. The supply will still maintain the equality sign because the situation happened on the demand side. So supply is still 600, but demand is more. So the one that is more, the demand which is more now will have a less than or equal to. Okay. The demand which is more will have less than or equal to. Now, why should it have less than or equal to? Ideally, it should be equal to, but why less than? Because the total amount that is going to be supplied is 600. And that total amount that is going to be supplied is less than the total that will be demanded. That's why you got to bring the less than or equal to. Does it make sense? Now, suppose that the total supply was rather more. If the total supply was rather more, then it's going to be what? It's going to be greater than or equal to. Okay. And so you got to be able to appreciate some of those things carefully. All right. So the total that is bigger, that's take the sign, less than or equal to. Yeah, it's the total that is bigger. So please note, if I said greater than or equal to, not that. If the supply exceeds the demand, the supply will rather be less than or equal to. And then let's make sense of that. Okay, suppose this supply was 700 and the demand is 600. So they are supplying 700, but these people are demanding only 600. So it means that there are some that they will supply that these people will not what demand. And so the supply must have less than or equal to, so that amount that, so less than or equal to the 700 that they will have in total, so that these people will have a pure equality. The demanders will have a pure equal to sign. So the one that is greater than, the one that is having the bigger number must always have less or equal to. Is having a bigger number. So if the supply is having a bigger number, it must have less than or equal to symbol. If the demand is having, it must have the less than or equal to. All right. One more thing. Prohibited routes. Prohibited routes. And this is important. Okay. Prohibited routes. Now, there are maybe some situations where it's not possible to route certain things in a transportation model. For example, road construction is there, so you can't move from Okonglo to Accra Mall. The road is blocked, and so the route becomes prohibited. Isn't it practical? The weather conditions are so bad that now we cannot actually. Now there's a strike going on in the area. So because of the strike, it's not possible. There's some unexpected floods, local traffic rules. So many of these things can make it difficult to be transporting things from a supply node to a demand node. We can handle such a problem in different ways. Okay. The first you can do is to assign a big number, a big cost, say M or infinity to that. Since the objective function to this route, you do that as the objective function gives, so that it never receives an allocation. It doesn't receive any allocation because of the high relative cost. So you give it a big value. Now, why do you do that? Because the thing is that if you force to break through the strike or the flood, that's going to be a cost. So in the model, you will assign a cost to it. That's one way. The other way is that you would delete the prohibited route altogether. So if a particular route, say X14 or X1A, okay, if that route is prohibited, you just remove it from the formulation. Okay, and when you do that, then you are sorted. See, all right. So at this stage, the model that we formulated, we can do it in Excel. And what I've done is I've copied and pasted what I did in Excel for you. So you can just follow the trend and do the same thing. So I've done it in Excel nicely here for you. Okay, these are the total demands. Okay, and these are the total supplies. I've done it in Excel. Just do the same thing. Okay, that's a model. And what I've done is that you go through that on yourself and then go through it and then you get a solution. Okay. This will take you through the cut and paste approach of getting it. And then you will now have how to use the solver parameter to get the results. And then you can find your final results here. In fact, these are the final results. Okay. So you have these as your final results. And I'm going to explain this pretty soon. Now, sometimes in an exam situation, I create the results. And I give you some questions like what you have here. So I'll ask you that your mathematical model was solved using the solver parameter, and some of the parts of the output are shown below. Okay. Use it to answer the questions that follow. What is the optimal solution to this problem? What is the total cost? Okay. So I'll show you the results. So this is the result, and then you are asked that question. Okay. What is the optimal solution to the problem? I mean, looking at these results, okay, let me just remove them now. Looking at these results, watch it here. Now we know that from Kansas to Cincinnati, we know that, okay, from Kansas to Cincinnati here, Kansas will have to supply. So X14 will have to be what? 25. And X16 will be 125. And that will settle it. That will settle it for that particular Kansas because they wanted to send only what? 150. So they've been able to do that. So the optimal solution would be for Kansas to supply 25 tons of wheat to Chicago, 125 to Cincinnati. For Maha to supply all the 175 to Cincinnati. And for DM to supply 175 to Chicago and then 100 to St. Louis. And when you do that, okay, you can now pick those values from 25, which is X1A or X14 in your case. So you come here, so you multiply this 6 by that value, 25. Wherever the answer was found, this 125, okay, let me see if I can zoom it slightly. So if you look at this 125 here, this 125 that you are seeing, that 125 is X1C or X16 that we have. So when you come to yours, okay, when you come to yours, that is this value. So it means that you are going to multiply the 10 by that. And when you now substitute whichever one you want to substitute for, surely you're going to be able to what? Find the exact total cost as you substitute these values into them. And that is exactly what I do here. And when you do that, okay, by the way, you can redraw the whole thing now and show those 25, 125. You can redraw it, which is part of the question. And then you can now say it as well. Transport 25 from Kansas City to Chicago, just as I indicated. And the total cost, you substitute them. Okay. So you substitute them just as I indicated, and you get a total cost of $4,525. So that is it. That is how you go through. This substitution is just like the normal linear programming where you substitute the decision variables into the work. And once you do that, that will solve your transport